Hello everyone, my name is Eva Rexigel. I'm a PhD student from the RPTU in Kaiserslautern. I hope my presentation is, oh yes, here it is. So I'm going to talk about the use of graphical representations of qubit. The first question that arises is, why should we even concern ourselves with graphical representations in quantum education? Well, I'm part of the project Quantuk at the RPTU, and as part of this project we developed a part-time master's program for quantum technologies for people in industry. And pretty soon in our work we realized that there are two main challenges in doing so. The first thing is that quantum technologies are a highly interdisciplinary field. We have various disciplines that come together to one and look at quantum objects, quantum properties. And another point is that we also have a heterogeneous group of stakeholders. Some of them may already have knowledge in quantum physics, others may not and be maybe totally new to this topic. So the main question we asked ourselves was, how can we enable really effective learning of quantum technologies for these people of various different qualification profiles? Well, and one important step to reach this goal is an appropriate use of representations. We know from educational research that we can support learning not only in quantum technologies but learning in general, also in different STEM disciplines, by incorporating not only symbolic representations, so not only relying on the mathematical formalism, like here in the context of quantum technologies, maybe the direct notation or density matrix formalism, but also include graphical representations, which don't rely on these symbolic descriptions, but use graphical analogies to represent quantum characteristics. Examples in this context are the 3D plot sphere or the circle notation. Now, when we are in the context of quantum technologies, we have some challenges we have to keep in mind. In contrast to classical contexts in classical physics, for example, learning based on prior knowledge, which is typically classic, is only able to a limited account. And in line with this, also the graphical representations are also often limited in their applicability. So many graphical representations can only be used to a limited extent and in specific contexts. And to support our educators, we decided to collate and analyze those representations that are commonly used in education courses, in higher education courses on quantum technologies. And in doing so, we didn't only focus on possible applications of these representations, but also on the cognitive requirements we have to keep in mind when we use these visualizations to communicate quantum technology content. And, well, two major things we found, two major results we found was first, of course, the mathematical formalism dominates in higher education courses on quantum technology, which is what we expected and which is totally fine because mathematics is the language of quantum physics and we can't just avoid mathematical representations. But we also found that graphical representations are already used actively to teach quantum technologies, but predominantly only in the beginning for the visualization of single qubit states. If we go further in the context and go on to more complex systems of multi-qubits, then we see that education here goes often back to relying on the mathematical formalism alone, which is an important thing for us to see as a difference here in the content. So in our work, we analyzed various representations which are used. Within this talk, I would like to draw your attention to two examples of these. The first examples I've brought is the 3D block sphere, which might be common to some of you. The 3D block sphere is a typical visualization. Here you have an example on the right. In this block sphere, we typically visualize a qubit state as a point on the surface of a unit sphere. On top of the unit sphere, we have state 0. On the bottom, here in the examples, we have state 1. And all the possible superpositions are lying on the surface of the sphere in between these two extrema. This block sphere is a popular representation in quantum physics to represent two-level quantum systems. And this might be also because it allows a one-to-one transfer from mathematical description to a visual representation. And it doesn't only visualize the mathematical description of a single qubit, but also the mathematics of quantum operations. It also has the advantage that it visualizes some of the main characteristics of qubits, which is, for example, the irrelevance of a global phase, which is naturally visualized here because of the symmetry of the sphere. However, when we use the block sphere in educational courses, we have to keep in mind that in order to really work with this sphere, we have to have spatial thinking ability. So in some contexts, it might be considerable not to rely on this three-dimensional representation, but to more focus on two-dimensional representations, for example, of this sphere. And another thing here is that if we go on to more complex systems of multiple qubit, some n-qubit systems, then it can be very complex to show these systems, for example, entangled states on the block sphere. This might be one of the main reasons why the block sphere is mainly used to visualize only single qubits. So another alternative, if you say, well, I'm not sure to use really a block sphere, then there are many alternatives to use here to visualize qubits. One of them is the dimensional circle notation. In this notation, we visualize each basis state of a given qubit system as one circle. The filling of the circle represents the amplitude of the corresponding basis state, and the phase of the respective basis state can be visualized by an inner pointer which is rotated inside the circle. So on the right-hand side, you can see an example for representing a single qubit. The dimensional circle notation, or the circle notation in its basic form here, has the advantage that we can visualize effects of operations on the single basis states, which can be especially interesting in the context of quantum computing. And we have also the advantage that we can go on to larger n-qubit systems by just adding more of these circles for each basis state that comes here. If we extend this circle notation to a dimensional arrangement, so in the example here you can see a two-qubit system with qubit 1 on the horizontal axis and qubit 2 on the vertical axis, we can use this dimensional representation to visualize entanglement. So one big advantage here is if we look at the symmetry axis in this arrangement, we can directly see if there's an asymmetry in this arrangement, that this system is an entangled system. I don't want to go further into this detail, but if you want to have more information on this or are interested in some discussion on this, then feel free to visit us at our stand behind there to discuss more about this advantage. Yeah. However, also in this dimensional circle notation, we have to keep in mind that if we go on to more systems, which is theoretically possible for whatever number of qubit systems you want to add, we have to keep in mind that with each qubit we add to the system, the number of circles we have to visualize here increases exponentially with the number of basis states, possible basis states. So these are two examples of possible graphical representations you can include when talking or educating quantum technologies. To conclude, I would like to keep in mind three major points. So, to support learners in quantum technology, don't solely rely only on the mathematical formalism alone. Incorporate also graphical representations, especially to introduce people from diverse mathematical backgrounds to quantum, not only those who have already prior knowledge in mathematical contexts. Then also consider different graphical representations. Don't necessarily rely on one representation alone to also account for the interdisciplinary nature of the field itself. And the third, last but not least, use representations consciously. Explicitly address limitations and connections between representations to enable that learners can really learn transferable and get in transferable knowledge. So with this, I'm at the end of my talk, and I want to thank you for your attention.